Okay, I'll make a start now. So, what I'm going to do this evening is to look at bending moment and shear force diagram from the point of that you have got a test tomorrow. So today I'll run it like more of a tutorial sessions where you can ask me questions, and if not, then I'll go through some of the tutorial material and then take questions from there. So to start, as mentioned before, tomorrow afternoon 4 o'clock you will have your third online test. Format would be very similar. So it would be half an hour test, and if you are bringing your own device, then you can choose to be here or take your device to the computer cluster. Now, computer cluster is not fully booked tomorrow, but there would be enough space there, I'm sure. If not, then we'll use the outside one, because that's booked for another class tomorrow, computer cluster. But I'm sure we'll find something there. And then again, those of you want a bit of isolations in terms of secluded space, those of you who have got, for example, extra time and would be disturbed here, then by all means go to the computer cluster tomorrow, because they have got the cubicles there where it's fairly isolated and secluded. And then of course that you have to sign the attendance register, and that's it. So half an hour time, and it would be the format would be the similar, maybe little bit more in terms of the calculation type questions rather than the multiple choice in test number 2. Syllabus would be whatever is covered in shear force and bending moment diagram. So in particular, you should go through tutorial 3 and tutorial 4. So tutorial 3 and 4 are the problems that you should be familiarize yourself. Now, having said that, it's it is probably unlikely that you'll get exactly the same problem, probably not. But if you can do these problems, then I can assure you independently, without looking at the solutions, then you will have no problem tomorrow. Now again, I emphasize again and again, when you get a problem in structures, try to solve it by yourself first. And that is the only way you can find out what is it that you don't understand, where is your conceptual difficulty lies. And if you can solve 1 or 2 problems on your own, then you will be able to solve the rest of the class of the problem. So it's as simple as that. So getting the concept is the main thing. The steps, and then how to follow, how to interpret that problem, what it is asking. Yeah, okay. So the question about sign convention I'm going to pick up in a minute. So try to resolve do the problem the way you would be able to do, and then only it will make sense. There is no point in doing 200 or 300 problems. I don't see the benefit of that. And you can pick up any textbook from the library, e-text. There are hundreds of problems there. You can look at examples, all the examples. Examples only teach you if it increases your understanding. And only way you can check whether your concepts are clear or not look at the solutions, but do the questions yourself. Okay, and again the questions would be different for everybody, different for each of you. So especially the numerical type questions and multiple choice questions also most likely would be different to different persons. So even if you are sitting next to each other, unlikely you'll get the same questions or the same format. Okay, so please be beware of that. Okay, and of course there will be invigilation. In terms of the sign convention, I am using a sign convention for a purpose that will be consistent throughout the course and will mostly stay on the positive sign as well as the practitioner's way of drawing bending moment and shear force diagram. Different books have got different sign convention. Now, in terms of if you are doing a problem here online, I'll mostly say ignore the sign, for example, to allow any sign conventions you may choose, for example. So if a bending moment according to my convention is minus 45 and according to your convention is plus 45, then of course I'd say in that case it is plus, just put the numerical values. But if I show you certain bending moment diagram, I show a beam and say, give a load and say which is the correct bending moment diagram. Now if I give that sort of a problem, I will put my sign convention next to it. Okay, so you interpret which one would be correct according to that particular sign convention. Okay, so if you are choosing your own sign conventions, which you are most welcome to do, then you definitely need to convert that whether that is same as my convention or opposite to my convention, and then choose appropriately. Okay, does that make sense? Okay, so that's about the sign conventions, what we say. And in terms of the sign conventions, this is our sign convention we choose. So load downward positive and shear force left side going down relative to the right side going up is shear force positive, and bending moment is a hogging bending moment positive. So the bending moment in such a way that beam element will bend upwards, and so it is anti-clockwise on the left hand side, clockwise on the right hand side of the section. So this is the sign conventions I will be used mostly, and for that you will get all these things as positive. dVdx is W, dmdx is V, and also most importantly it draws the bending moment on the tension side of the beam. So and that's the industry standard. So if you join industry, and most of the software for structural analysis will draw the bending moment on the tension side. So at least for the beams you will see that. So many cases, many books it will draw the bending moment in this direction. So this would be a negative bending moment for them, they'll draw it downward. But that's not the industry standard in that sense. So, but that doesn't mean it's wrong, as long as you are aware of that is the sign conventions that they are using, or that particular book is using. Again, there is a difference between US books and British books. So British books primarily use this sort of sign convention drawn on the tension side, but again there is a variations between these two. So I'm happy with any sign convention you choose, but if I give you a sign convention, then follow that. So in terms of the sketching the shear force diagram, I'll probably give one or two example problems there and show some shear force bending moment diagram, and you have to click which one is the correct shear force or correct bending moment diagram. So that will be one type of questions, and then probably majority of the marks would be concentrated on bit on the numerical problems. So you'll be given a problem and then shown where so find out bending moment at a distance. Say if I give a problem like this, and I say, of course the load would be different for different candidate, and the distance could be different, and then I say, okay, find the bending moment at these particular locations. So you have to find the bending moment at that particular locations, and I'll probably say give the value in kilonewton meter and don't bother with the sign. So even if it is your sign or my sign, it is giving negative, don't put the negative, just put the numerical values. So it will be that type of question. And if I say, okay, using this sign convention, so I can give you my sign conventions like this. I can say using this sign convention, write down the bending moment at that locations on the right hand side. So that is the possibility of the questions there. So that's about the tomorrow's test. So this is quite an important component of the course unit. Make sure that you revise well and then come prepared for the test tomorrow. In terms of these questions, I realize that you have got solutions for these, but not for that one, right? So I started making the solution, so I'll probably go through these solutions now, unless you have got any questions from tutorial 3. It has got all the solutions, I believe, in Blackboard, or first part of tutorial 4. So do you have any questions related to 3 and 4? Okay, so the axial force diagram, yeah, okay. So some problem where you have got a horizontal component of the load, for example here. So you have got an it is a possibility of having an axial force diagram. So in this case, for example, for that problem, you have got here, that's the load, and then this is the roller, and you have got a load here. Now this load, you can divide it into two parts. So one vertical load, one horizontal load. So the axial force diagram could be, so from here to here there is no axial load. So this axial load only comes from this side, and this is compressive in nature. So if it's a compressive, I'll put negative. So if this force is F, for example, then that doesn't vary, and that will be constant up to here, and which will be balanced by the force there. So this is the axial force diagram, and it is F, and with a negative side, you can say negative is compression. Okay. Okay, what is your question? 2 rows back. Yeah?
I also wanted to ask about axial force diagrams, but how do you do axial force diagrams where there are 2 or more?
You have to start adding up and adding up algebraically. If they are going in the same directions, you add them up. If it is opposite directions. So for example, if you have a beam, something like that, and you have got 2 loads, just I am drawing the axial directions. So you have got one load here going this direction, say 2 kilonewton, and this point it is going that direction, say 4 kilonewton, and that point it is going this direction, say 5 kilonewton, let's say, like that. Okay, so when you are drawing the axial force diagram, so you could say, okay, from here to here there is nothing, so that comes down like this, and from here to here 2 kilonewton. So 2 kilonewton compressive, so go to 2 kilonewton, and then it is creating tensions. You first of all think about what would be the reaction force here. So 5 this way, 2 this way, 7, and 4 in that way. So that means there is definitely 3 kilonewton reaction force in this direction. So that is 3 kilonewton in this direction would be the reaction force, because that would be this force, and that force must be balanced by these 2 reaction force onto this side. So this is 4, and then that is going to create a tension. So this is 2 minus 2, and then that would be 4, because that's on the opposite direction, and then comes there, and then that is 5 coming down into 3 unit in there, and then again here is 3. So that is like axial force diagram for this case. So you just add and subtract as it is.
What if it's the beam is two dimensional?
Beam is?
Two dimensional. It extends from the
So it's a sort of a frame.
like off the edge.
So beam is like a frame. So again, if it is a frame, then what you need to do is, then axial force and shear force will have different meaning. So if you have got a frame like that, and if you have got a load acting at an inclined direction, let's say this is the load. So this load, definitely you need to think about two different ways. So for example, this load you need to define, one is horizontal and another is vertical. Then you can delete that load. Okay. Now what about this green load? So the green one, if you consider this beam, this part of the frame, so the vertical part of the frame, the green load will cause bending plus shear. Okay? The green load on this part will cause bending and shear, whereas this one will cause axial force. Okay? Now, for when it comes to these upper segments here, when you get to this beam segment here, then this force is, you can consider it is going into directly there. So this will cause shear plus bending. What about the green one? Green one would cause axial plus a constant bending. Because this one, if you transfer to there, that will have a bending at that point. So the green one would cause axial plus a constant amount of bending onto this one. So you have to just take into how this will constant bending, because if you take a section at any point, due to the green component of the load, your bending moment is always that load times this vertical distance, and that would be anywhere along this beam. So that's what this is, the constant bending. Is that okay?
So in that sense, the horizontal beam will never have zero bending.
Not zero bending. Why zero bending?
So it will always be.
So it will have bending due to this, bending will increase due to this blue load, plus there would be bending due to a constant amount of bending due to the horizon, the green load. So not zero. Why that would be zero?
No, so it won't be zero anywhere.
But this blue load will increase the bending as you go along. So it won't be constant. For the green component, it will be constant bending moment. So if you take bending moment at this point, what is the bending due to the green? The load times that distance. What is the bending moment due to the green? Blue. The load times this distance. Now take another section here. Bending due to the green does not change because the load times the distance did not change. But the bending due to the blue would change because the distance has changed. So the bending will not be constant along the beam. Okay. Any other questions from the part 3 here? You get this 3 tutorial sheet 3. Any more question on this? As I said, if you understand the tutorial questions, you should not have any difficulty. But I am unlikely to put exactly the same question, if that makes sense. It won't be necessarily complex. It would be different. It won't be necessarily complex. Maybe you will find it simpler. Okay. Yeah, all these questions in the tutorial, I want you to get hang of those independently, without looking at the solution. Okay. And if you can get that, then that's fine. That you should have no problem with the test tomorrow. So that's tutorial sheet 3, tutorial worksheet 3. I'm going to look at number 4 if I can. Is there any questions on number 3? No? Do look into the solutions for number 1. So if you move from the right to left, then the slope would be different if you go from left to right. So make sure that you are aware of that. So in terms of tutorial sheet 4, do you have any questions on first 7 questions before I go into 2A? Any for these solutions are there? Any one of these that you don't get? Yeah? C. D. This one. Okay. So the question is this one, because there is a triangular load. So the question is what to find the also location of the bending moment and its value. So as we have got the solutions, I will go directly to the solution, and then so 2 meter, 5 meter and 5 kilonewton per meter is the intensity of the load here. So in terms of the solutions, so the first thing you need to find out the reaction forces. So the reaction forces is the first thing of this problem. So how do you find the reaction forces? Now if the load is like this, first of all you need to know what is the total amount of load. If the load is distributed, you need to find out what is the total amount of the load and where do the load act. If it was an uniformly distributed load, you will find that it will act at the center of the load train. It will act at the center of the load train. And concentrated load, you know where they are acting. But when it is a triangular load, first thing is you need to find out what is the amount of the load, and second thing is you need to find out what is the action point of the load. So the first thing if I see what is the total load. So the total load for a triangle is area of the triangle. So half the intensity of this side, which is 5, times the distance along there, which is 2, and that much kilonewton. So the total load is 5 kilonewton. Now this is 5 kilonewton per meter, so total load is 5 kilonewton. So this whole triangular load is 5 kilonewton. Okay? Now where do this act? This will act at the centroid of the load. So the load is shaped in a triangular variation. So it will act at the centroid of the triangle. So the centroid of the triangle is always 1/3 from the base. So if this distance is 2 meter, that would be 2/3 meter. And conversely, this side would be 2/3 of 2 meter. So this would be 4/3 meter. So that if you add these two, that will give you total is 2/3 meter. So these are the two things first you need to know for any load. How much is the total load and where do the load act. Otherwise you can do an integration, but this is the easier way to do that. So we'll assume this 5 kilonewton load is concentrated at that point, at the centroid, to calculate my reaction force. So to calculate the reaction force, I can take moment about point A equal to 0. Then I have got R2 is the reaction force, and this R2 is creating moment in this anti-clockwise fashion, and it is at a distance 7. So that's why R2 times 7 and with a minus sign, because that's going anti-clockwise. And then the load due to this triangular one. Now this is the total load, as we said, that is 5 kilonewton, and this is acting at a 2/3 meter. So it is acting in a clockwise direction, so that's positive. So that will give me R2 is 0.48 kilonewton. Next, to get R1, either you can deduct from the total load of 5 kilonewton this 0.48, or you can take moment about point B and get RA. So either way you will get R1 is 4.52 kilonewton. Next is what you need to do. The bending moment diagram and the shear force diagram. So if Z is less than 5, so in this case I could approach from the left or the right. In this case I said, okay, I'll take a distance Z rather than X from the right hand side, and I'll take at these locations. So if I make a cut, I will have a shear force and bending moment at the cut location. And you have to use the same direction as your sign convention. So it is going downward and up. So if you take equilibrium of these, you will see V would be this direction 0.48. So that's the right chosen direction. So that's a positive shear force. And moment would be 0.48 times Z and with a minus sign. Now if Z is more than 5, or in other words in there this point, then you will have this little bit of triangular load comes into picture. So that is the reason I came from this one. If you come from the left hand side, of course that would be a trapezoidal load. So you have to consider centroid of a trapezoidal. So centroid of a trapezoidal, always, if you cannot avoid sometimes, center of a trapezoidal load, say if you have got a load like this, say it's a triangular load you have got, and let's say you are considering only up to here. So you have got a trapezoidal load from there to there. You want to find out where is it centroid. What I will say is you divide it into two triangles. You divide it into two triangles. So one triangle that and one triangle this. And that would make life easier. Okay. So I didn't do that in this case. I have still gone from this. So what would be this load intensity if I go at a distance Z from the right hand side? So this up to here is 5 meter, and if I go up to a distance Z, then this little distance is Z minus 5. Now what is the slope of the load? The load intensity become 5 kilonewton per meter over a distance of 2 meter. So the slope of this load is 5 over 2 kilonewton per meter. So the load intensity increases at 2.5 kilonewton per meter. So at a distance of Z minus 5, this load intensity would be the slope times Z minus 5. So this intensity here is 5 over 2 times Z minus 5. So first of all find out what is the load intensity, the slope of the loading, and then you find this one. Once you get that, then you again find the total load and its centroid, and then find out what would be the values of this load. So once you get these expressions, and then finally you can draw the bending moment and shear force diagram using those expressions. So it's just the algebra gets a little bit complicated rather than the concept wise. Which bit you are not sure about?
So just the Z minus 5.
Is that okay now? Yeah? That's fine. Any other questions on this? Yeah? Okay, so there is a problem in here, isn't it? Yeah. So I'll go through that in a moment. So this morning this afternoon I've started to solve those. So I'll go through that in a moment. Any other questions from A to G? No? A to G is okay for everybody? I may expect. Oh, okay. You have got a question. Trapezoidal load I'll cover in 2C. Okay? 2C you'll have a trapezoidal load. I'll cover that. Okay? So if you tell me you are okay from A to C, I'll expect 100% tomorrow. Okay, good. So good thing. So that if you get it, these are basically concept wise. That's it. If you other problem just becomes algebraically complicated rather than conceptually complicated. Okay, so I didn't realize that you didn't have the solution for this. I'll upload the solutions tonight, but I'll go through some of these problems. So first I'm going through 2A, then quickly 2B, and then 2C. So 2A, you have got a simply supported beam and then a load incline and 1 point. So I'll go through that quickly because that's fairly straightforward problem. So what you need to do in this case is to resolve that load, a vertical load and horizontal load. And to draw the shear force and bending moment diagram, you can ignore the horizontal component because that does not contribute to the shear force and bending moment. It does contribute to the axial force, but that's it. It does not contribute this horizontal component to any shear force and bending moment diagram. So you have got now a beam with 2-point loads. So exactly you approach in the same way. You take a distance at x equal to less than 4 meter, find out the shear force. Anyway, I'll upload that in the evening. Once I go home, I'll take a scan and put that in. And then you can put for different cases and draw the shear force and bending moment. So conceptually, it is just dividing that load horizontally and vertically and then ignore the horizontal part to draw the shear force and bending moment diagram. Okay? So that would be the shear force bending moment diagram. Okay? So the next one is this questions, and here you have got 3 loads, 1 UDL, 1 point load and 1 a concentrated moment. So there are 3 loads in here. So again, first of all, try to draw the first is find the reaction forces. So make sure that you get these values and so take moment about this point. So if you take moment about this point, let's say this point is A. So if you take moment and that, let's say this reaction is RB or something and this reaction is RA. So if you take moment about point A equal to 0 for all the forces. So how many loads you have got? You have got 10 kilonewton load going through the whole beam. So how much load that is? 10 times 12. That is the total load. 10 times 12. That's the total load for the UDL. And where does it act? It will act at the center of that load train. So center of the load train is 6 meter from the left hand side. That's where you are taking moment. So that is 6 meter. Is it going to be clockwise moment about point A or anti-clockwise? Think about it. So if this is the moment, this is your pivot, this load will make it clockwise rotation. So this is a clockwise rotation. So I'll put a positive sign. Now remember, when we are taking moment equilibrium, the sign convention is different than sign convention we choose to draw bending moment and shear force. Bending moment, shear force, sign convention comes in pair. The left of the cross section, right of the cross section. So this is different as from the sign convention as when we are calculating moment equilibrium of the whole whole beam in that way, or the free body. So this is equilibrium equations that we are doing. So that's the UDL. Then 36 kilonewton load. 36 kilonewton load acts at a distance of 4 meter. Clockwise or anti-clockwise? It is a clockwise moment. So that's a plus sign. Then 60 kilonewton meter moment itself. Now there is no distance we should do, but that is clockwise again. So this moment is acting clockwise again. So that is plus 60. What about this reaction RB then? Now this reaction RB is going to rotate the beam about my pivot point at A in anti-clockwise direction. So RB times the distance is 12 meter. That's anti-clockwise, so I'll put at a negative value. So that will give me value of RB. Once I get value of RB, I can find RA by using summation of vertical forces 0 or taking a moment about this point. So you'll get RB as 77 and RA as 79 kilonewton. Okay? Is that okay? So once you get that, then you can take a cart at different locations. So you can take a cart here, for example. So x is less than 4 meter. So you have got 79 kilonewton load and 10 kilonewton per meter load. Then you can get an expressions like that. Then you take a section at here. So x is between 4 and 8 meter. Then you get two of these expressions. Then you take over here, and then which is x more than 8 meter and less than, of course, 12. Then you get these expressions. And then you finally complete, just draw these bending moment and shear force diagram. One thing to note, or rather two things to note: maximum bending moment will occur where there is a zero shear force, and when there is a concentrated moment, there is a jump in the bending moment diagram. Very similar to when there is a constant force or concentrated force, you get a jump in the shear force diagram. Same is true if you have got a concentrated moment, you get a jump in the bending moment diagram. You get a jump in the bending moment diagram. So again, this is fairly straightforward in terms of the concept point of view. Again, this maths bit, the expressions bit, you have to work it out and do things, but other than that, it's fairly straightforward. And also another thing you should note, that whenever there is a hinge end point, bending moment is 0. So you should never put bending moment at a pinned end at the end. And if it is a fixed end, then of course there could be bending moment. So that's problem number 2. Problem number 3 is where you have got two triangular load and one UDL in the middle. And also, to make the problem a little bit complicated, there is this load at 5 kilonewton per meter intensity, and this is 3 kilonewton per meter. So it's fairly numerically or rather complex and challenging in that point of view, but I'll go through that, and that will answer your trapezoidal question as well. So if you do the free body diagram and calculate the total load and where they would act, then you will find out these reaction force. So if I do the left hand side total load, so the left hand side total load would be half times 5 times 3. So that is the left hand side total load, so that would be 7.5 kilonewton. And that will act at a distance of 2 meter from the left hand support. So 2 meter from the left hand support, that's where this left hand side force would act. So 7.5 kilonewton will act 2 meter from the, because that's 2/3 of the 3 meter. What about the right hand side? Right hand side total load is half times 3 times the 3 meter. So that is equal to 4.5 kilonewton. And where that will act? That will act, so this is the roller, and that will act at a point here which is 2 meter. So that is 2/3 from that point, so that is 3 meter. So 4.15 kilonewton will act from that point. So if you take these two, and you know this load, the middle load is here, that's the total load is 4 times 10 is 40 kilonewton, and that will act in here, which is half of 2 plus 3, so 5 meter from this side, and then also 5 meter from this right hand support, left hand support. That's why this middle 40 kilonewton would act. So triangular load, total load is half at the maximum load intensity times the span, and that will act at the centroid of the triangle. Centroid of a triangle is, so if you have got a triangle like this, its centroid is, if this distance is d, then that distance is d over 3. And of course then that means this distance is 2d over 3. 2d over 3, that distance is. So that if you do, that will give you these two reaction forces. Once you know the reaction force, then you start taking the cut. So if you take a cut at a distance x from the left hand side, or x less than 3 meter, then the load intensity at a distance x would be 5 over 3 times x. How do I get that? Now of course, to get that, you need to think about, this was the load. Like 3 meter if it goes, I'll have a load intensity of 5 kilonewton per meter at a distance of 3 meter. So the slope of this load is 5 kilonewton over 3 meter. So 5 kilonewton per meter, 5 over 3 kilonewton per meter length. So if I go at a distance x from left, this load intensity would be the slope times the distance. So slope is 5 over 3, so 5 over 3 times x. So in other words, if it is x is 1 meter, then that would be 5 over 3. If x is 2 meter, then that would be 10 over 3. If x is 3 meter, that is 15 over 3. That means it is 5 kilonewton per meter. 15 over 3. So that, once you get that load intensity, so at a distance x, that is the 5x over 3. So the total load of these segments then would be half 5x over 3 times x, so 5x square over 6. And the centroid of the load would be at a distance 2x over 3 from the left, or x over 3 from the cut position. So x over 3 from the right hand side. So shear force then would be 26.9 going up, so that's a negative. According to the left hand side, if it goes down according to my sign convention, that's positive. And left hand side, if it is going up, that's negative, so that's why minus 86.9. Plus the load due to that one 5 going down, so that's positive. So the total load is 5x square over 6, so that's it. Moment similarly due to two loads. So the moment due to two loads, one load is due to 26.9, so that is minus, why minus sign? Because that moment will create in this way, clockwise. Now what is my sign convention at the left hand side moments? Anti-clockwise is positive, so that's why negative sign. And then moment due to this is anti-clockwise, so that's positive, that gives you 5x cube over 8. Now when you go for the next one, if you take the section over here, so part of the middle bit is there, so the load train would be something like this. So you have got the full triangular load plus beat of 10 kilonewton per meter. So the total load would be, for the triangular bit is 7.5 kilonewton, and it would act at a distance from this point is, it will act as a x minus 3 plus 1 meter. So that is x minus 2 meter. And then you can draw the shear force and bending moment diagram, bending moment values for these two loads. Finally, if you take a section at a length which is here, if you take a section at this point, then your load train would be something like this. You have got a full triangle plus UDL plus a bit of trapezoidal load. So bit of trapezoidal load, I've drawn it slightly separately. So at this point it is 3 kilonewton per meter. At this point it is 10 minus x. So I have divided that into two triangles. So triangle number 1 shown in purple, is the total load is half 3 times x minus 7. The triangle number 2 is in green, total load is half x minus 7 times 10 minus x. And where they will act, the first one, it will act as a 2/3 from this point, is 2/3 of x minus 7, and for the green one would act 1/3 of x minus 7. So once you get that thing, then you can write down the shear force and bending moment expression. Now this is fairly complicated, I am not denying that, but the point is in this way. So if you have got a trapezoidal segment, for a trapezoidal segment, instead of finding the CG of a trapezium, just divide it into two triangles, and the triangle, you know the area as well as its CG, and then you can use that two separate ways. Who asked this trapezoidal? Is that okay? So shear force and bending moment diagram will, once you find the expression, then you vary the x value, and then you can draw the shear force and bending moment diagram. So x in this case is from 7 to 10. So you put in x equal to 7, you will find the shear force value at 7 meter. Then put x equal to 8. Yeah, so no, shear force not necessarily would be 0. Shear force at that end would be that reaction force, whatever, 25.9 or whatever we got. Louder, please. Yeah. The question is, if you have got a trapezoidal section, if you have got a trapezoidal load, can we do it in terms of a rectangle and a triangle? By all means, yes. By all means, yes. Okay, so I am going to put this in blackboard, but finally I have got these questions. This is also similar. This question, if you can pay some attention, please. What do you think you will be doing for this case? Absolutely, that is one way. So the question is, the beam is tilted. Now what about the shear force and bending moment diagram? Now if you do the reaction forces in this case, you can get the reaction forces vertically, but then the shear force diagram is always shear force is perpendicular to the axis. So there are two ways you can do. You can have that beam loaded, you can find out the reaction forces, and then these reaction forces you divide it into perpendicular to the section and the horizontal to the section, and then draw the shear force and bending moment diagram. Or to start with, what you do, you make that load horizontal and vertical. You make that load horizontal and vertical, and then take the shear force and bending moment diagram according to this. So that is also another way you could do. Okay. So I'll upload this to these few other questions that are there, but good luck for tomorrow. Okay, thank you.
I just want to be clear on something.
Yeah.
Do you know when you have the, sorry, just yours. So when, is that?
That's the other way around, yeah.
Is it all the way around? Oh, okay. But that diagram, is that when, say, if you took a cut and it's where you're using the left-hand side from the cut?
Then you consider these are the possible.
And that's if it's right-hand side of the cut?
Yeah.
So,
Yeah.
So if it was like you're taking the cut there,
Yeah.
then you use that hand side, and if you're taking the cut from there, you use that hand side.
So basically, if you have got a force, so this is 3.6 kilonewton, and say this is 5 kilonewton, and then of course that is this. So you have to have shear force in this direction, and this is your positive shear force and positive moment direction. Okay, because you have made a cut at the right hand side.
So you made, but from the left.
Yeah, because you have made a cut. So cut on the right hand
So
side.
so I was almost imagining it as if like the beam would be coming from that way, and then like you imagine it so that that's. On
So
the right
it's on the right hand side of the section. So, but if you had cut the beam from this side, this is 1.4 kilonewton, then it is on the left hand side. This is the positive direction of shear and moment.
The other question I had was for our structures course, we're doing like capacity before. If we wanted to consider the self-weight of the force, on like a free body diagram, we could just draw that as like a load about its centre of gravity, and
Yeah,
then
yeah.
just treat it normally
Yeah.
like a shear force diagram.
Yeah. That's just a point. Or you could say distributed load as the middle, because if you take the forearm, it's
Yeah,
not
that's
fairly
what we were-
fairly prismatic. So you could
Yeah.
say, okay, wherever its center of gravity of that load would be, that's it. Or bending moment could be changed. For
Yes.
example, bending moment due to point load and UDL are different. So that bit.
Sorry, I was wondering, so for a geometric exam, there's going to be questions that are going to be like diagrams, and then there's also going to be calculation questions. But,
Yeah.
like, what's like the split on it? So is it going to be like mostly diagrams or mostly calculations?
I haven't actually said the questions yet, so I won't be able to say, but it will be a mix.
So like 50-50?
Probably more would be more marks would be for calculation.
More much will be for calculating?
Yeah.
Okay.
Yeah, because that will take more effort. I'll just distribute the marks according to the effort it may take here.
Okay, so if there's going to be questions that are worth more marks then?
Yeah, of course. Not all, like before you have seen, the
Yeah.
questions are not equally marked. So the questions where you have to have either a difficult concept or you have got a little bit more calculations involved, that would carry more marks.
Alright, thank you.
Whereas sometimes the multiple choice questions also you have to think, or you may have to do a little bit of calculations. So I award the marks in terms of the effort that you have to take or the time that will take. So 30 minutes, 100 marks. So like that. So I'll probably do 25 minutes, 100 marks. So or maybe 20 minutes, 100 marks. So per minute, 5 marks.
But like tomorrow's exam is going to be 30 minutes, right?
30 minutes, but I normally give a little bit more time
Yeah.
because I know